All right, so we're going to start with number 7. A block did 7, but we'll do it again. That's good. It's identical to that pendulum one that we did yesterday in the example problem. Almost identical. So you'll hopefully see a lot of parallels between what we did yesterday and what we're doing today. Huh? Good? You ready to read it? Okay. All right, so we got a pendulum, and it's moving to the right at point B, which is its lowest point. You guys remember, just not loud enough to distract me. I am easily distractible. No air resistance is negligible, so no external work being done on it. And they want to know what's the gravitational potential energy when the bob reaches point A. I'm going to call point B 0 for the gravitational potential energy. That way, the change from B to A will just be from 0 to something. Make math easier, right? That's what our goal is, make math easy. And then also, what is the speed of the bob at point A? So A must not be the top of the swing. It must be on the way to the top. Or on the way back down, right? Good. So that's what's different about this one than the one we did yesterday. Yesterday we went from the bottom to the top. Now we're going from the bottom to someplace. So this is number 7. All right, so I know there's PE grav, right, at both places.
Are we counting air resistance?
Well, let's see if it told us anything about that. It says air resistance is negligible, so we shouldn't. That means that, and that's one of their code ways of telling me there's no external work being done here. What does work on it as it goes from the bottom towards the top? Gravity, but that's part of our system, right? Yes? Because the Earth is part of our system in this. So I'm going to say that it has a lot of kinetic energy there at the bottom. I already said I was going to call the gravitational energy 0 at that point, so we will. No external work, they told me that. It's going to have less kinetic energy. I'm going to say only 4 rather than 6. And it's going to be higher than it was before. So I'm going to give that. And now I just check. Yep, energy is conserved because I have 6 blocks on the left and during and 6 blocks on the final. Yeah.
So is point A not where it stops and moves back the other way?
Right, that's what I'm assuming because
So if that was where it stops, all the way from 0.
correct, completely correct. Well, because I'm making the assumption, it might be a bad assumption, that since they asked me for the speed at that point, then it's not going to be 0. It might be, but for now, I'm going to assume it's not. Okay? Just like, does it matter if I have, could I swap the KE and PE here on the right side? Yeah, because I don't know which one's more. I'm just kind of arbitrarily picking.
But if we did, like, KE like we did on the left and put it all in PE on the right, would that be wrong?
In this one, I would say that would be less than correct. Like if I was grading it out of 10, you'd be 8. Because you didn't give the possibility that it was still moving. You locked yourself into it's not moving, which is probably not the case. So you give yourself some flexibility this way.
So as a hypothetical, if you have a pendulum, you start swinging it, and it goes all the way down here where it has no potential energy and all kinetic energy. And then it goes back up, let's say to the middle where it's half kinetic, half potential. Then you stop it. Would that potential energy instantly switch to kinetic as it cuts off half of that energy and then start going the other way?
Yeah, because you'd have to do work on it to stop it. So you couldn't stop it instantaneously, you'd have to move a little bit. And so it would take away whatever kinetic energy it had, leaving it with just that gravitational potential. to go back down. What's kind of neat is if you transfer that, if you let it swing down, you have a rod, it will change the length of the pendulum, so changes the way it converts kinetic to potential. And so it'll go up differently and then come back and be the exact same. Yeah, because like ramps, lengths of the strings of pendulums are all just about what rate do you convert potential to kinetic and kinetic to potential. So if you mess with those, you just mess with the rate, not the amount they have. Within parameters, of course. All right, so remember these lead me directly to equations. So directly in my how, PE, oh, sorry, I did that first block also, I don't know why. KE at B equals KE at A plus KE at A. PE at A. Wow. Classes are just too fast today. I'm going punchy. Right? And that's, my bar graph said that, so my equation says that. Then I grab my handy-dandy equation sheet and pull off that KE is 1/2 inertia speed squared, and PE grav is the gravitational force, otherwise known as the weight, and the gravitation and the height. Right? Those are just from the equation sheet. Our handy-dandy friendly neighborhood equation sheet. I'm going to do a little drawing because that's the only way I can organize my brain. Oops, I don't know what that. I have my pendulum bob hanging down, and then it's up here to the side. They tell me that's 35 degrees. What's the length of my bob? 1.2 meters. So that length is 1.2 meters. This whole thing is 1.2 meters. If I do a perpendicular here, this little distance inside there, that little kind of, I think of the tail of the triangle is h, right? The change in height of the pendulum bob. We did that yesterday, right? A little geometry, a little trig, all that math fun. And if you remember from yesterday, we said that h equals 1.2 meters minus 1.2 meters cosine 35 degrees. Right? Alright, so all that's background. And what am I actually looking for? Okay, so, and the speed at point A, right? Okay, so I want to know P sub E at A, P at A, and then the speed. So I think I'll do P at A first. Is mgh, of course, where m is 0.23 kilograms times 9.81 newtons per kilogram. And then my height, I need to move all this over. Get over there. Not misbehaving. 1.2 meters minus 1.2 meters cosine 35 degrees. And that'll give me PEA. I wonder what that'll be. I got 0.489656691 joules. And that's not all they wanted though, right? They also wanted the speed of the bob a day. So I need to use that information now. So to do the speed of the bob, I'm going to do this equation. And I'm going to rearrange it so that I have my KE at B minus my potential energy at A equals my kinetic energy at A. Algebra, right? 1/2 inertia speed at B squared minus 1/2 inertia, the weight mg times h equals 1/2 inertia speed at A squared. Now I've got a choice. I know what PEA is. It's that number, right? So I can just put that in there, and then I can fill in the rest of my variables. I'm going to kind of ignore it. What if I screwed up that number? Then I'd screw up this one too. So I'm going to ignore that I know that number. Okay? And that way I can get rid of all my m's and multiply each side by 2. So I end up with VB squared minus 2 GH equals VA squared. Got rid of the m's because I had 1 in every term. Multiplied both sides by 2 because I don't like fractions. They betrayed me once, so I'll never let them live it down.
When did it betray you?
It was when I was in 4th grade. They let me down. I've never been able to forgive them for it. When I became a decimal man. Let's see, they tell me the velocity at B. For me, it's 2.6. Make sure you check your numbers, because it may be different. Minus 2. I know we're on the Earth, so 9.81 newtons per kilogram. The height is at 1.2 minus 1.2 cosine 35 degrees. Meters. And that equals VA squared. Most top. Don't forget to take the square root to find VA.